Yeah, so it has started recording. So good morning once again to all of you. So in the last class, what we have discussed, maybe we can do a quick recap of that. Okay. So we have started our discussion on this MOS inverter, and we have also discussed that inverter is one of the most fundamental digital gate, right? And if we know how to design an inverter, then those understanding or those concepts can also be applied for other much more complicated gates, right? So fundamentally we should first understand what is this inverter is and how to design this inverter and what will be the consequences if you change any parameter in terms of its power dissipation, delay, primarily on these two stuffs. Hmm? So here we have introduced the term voltage transfer characteristics, which is nothing but the output, V output versus V input characteristics of a particular digital gate. And we have discussed for ideal inverter, it should be like this, the black one, whereas for this practical one, or this should be somewhat in this, like shown in this ash color. However, it might differ depending on your design, right? This position, right? As I have mentioned this, do you remember what this point is called? This is the threshold of that inverter, right? Digital gate. So the threshold voltage can change depending on the design of this inverter. So then we have discussed one basic NMOS inverter. So it is a generalized diagram where you can have a load here and followed by in the below you have an NMOS. Right, this load as simple if you have to replace something, this load with, then at first what comes in your mind probably the resistance, right? So replace this load with a resistance and that's how you are getting this diagram, the second one, right? Okay, so here we have also discussed why the load is a capacitor, because one of the inverter probably it is driving another inverter or maybe some different gate. So while the input of this gate means input of the gate is basically the gate terminal of a MOSFET. So gate terminal of a MOSFET is associated with the capacitance, and because no current can flow through this oxide, so the IG would be zero, right? So no current would flow through this. Only during the charging and discharging, that dynamic, that thing will be there, right? Otherwise, there will be no steady state current, right? So that's why we have introduced this term CL, right? So we have also discussed what is what do you mean by this pull-up network and what is pull-down network. Pull-up network is basically this part through which the capacitor get charged, and this V out will increase from 0 to VDD. Whereas the pull down network means the network through which the capacitor get discharged, the load capacitor, and this V out, that is the output voltage, will change from VDD to 0. Next, the typical VTC of an NMOS inverter. On this topic, we have discussed how to get actually that VTC from a simple ID VDS characteristics and its circuit in and from its load line, right? So we have seen that yesterday. I think that is should be quite clear. If you have any doubt how you have got it, you may ask, right? Then we have seen like the typical VTC of and resistive load inverter may look something like this, whereas this point should be this VDD and this point would not be equal to 0, but it will be has some finite value depending on the design. Here we have introduced also mentioned that up to this point the transistor would be off, so there will be no change in this output voltage, right? This is VTN, this is the threshold voltage of this NMOS. So it will be constant. After that it will fall and fall rapidly, and then it will try to saturate. Then we have taken this in the next page and we have discussed some of the important points. For example, here we have mentioned this particular point, the highest value here. We have termed it as VOH, right? And the minimum point we have termed it as VOH dash, and the minimum point as VOL dash, right? And obviously here this voltage is 0 and this voltage is VDD. That is, you know that because we are switching this gate. So when you are applying the any voltage here, so you are it's a digital, right? So it is like it can go from 0 to the supply voltage only, right? Here we have also introduced the term that there will be two, when the curves will fall, this particular VTC will fall, then there will be one point where the slope would be negative, and where the slope would be negative we have similar, I mean we will get two such points. One is here and the another one is here, right? And we have termed these two input points as VIL and VIH, right? In this output axis, we have termed those points as VOH and VOL, right? So these are the couple of important points that we have discussed yesterday, right? And we have also discussed here the slope would be less than means mod of slope would be less than 1. Here the mod of slope would be greater than 1, and here the mod of slope would be equal to 1, right? Here again it will be less than 1, right? So only in the mid region the gain will be quite high. And we have also mentioned we do not prefer to operate any like in digital gate, particularly in this region. Right. So we have also discussed how do you define this VOH. So VOH is the, for example, the minimum output voltage to be considered as logic 1. VOL is the maximum output voltage to be considered as logic 0. Similarly, for same thing goes for VIL and VIH. So now if you see your book, like both Rabe as well as Kang, then you might see little bit difference in terms of its definition, because what they have considered in couple of cases that you will find. So please take a note that they have considered a VTC something like this. Okay, so here this point, that is this VOH dash, the point we have mentioned here, VOH dash and VOH, they are the same, right? Same value. So they have not distinguished these two in a separate way. They have directly mentioned this as VOH. Same goes for here. This point and this point has the same value, so they have mentioned it as VOL. But as you have understood that this point and this point would practically would not be at a same voltage level. So there will be some difference between these 2 points, and we will also do some numerical example then later to see that what is the difference between this point and this point, right? So please take a note that well, if you are reading from the book, you might see little bit difference in terms of this definition of this VOL. Sometimes they VOH and VOL. Sometimes they have defined VOH as this point only. Okay. So here we have introduced another important concept, which is the concept of this noise margin, and we have seen that from these two, from this particular circuit diagram, where one inverter is driving another inverter. So here we have seen the output voltage of this inverter. The valid output voltage lies between this band. Similarly, if the logic is output, if the logic is output logic is 1, right, then it should be in this band. If the output is of logic 0, then the output would be in this band, right? This is the valid band. Anything between this is not valid in terms of this gate. Similarly, for this particular gate, the second gate, for the input, right, the valid input voltage for to be considered it to be as a logic 1 is this much, right? Then definitely, this much error or this much noise, this gate can still handle. Means if the noise level is within this, then also that voltage, particular voltage, will be considered as logic 1 input for by the next gate. So this here, this voltage level is called the noise margin high. Same thing will also be there for this noise margin low. So that way we have introduced the term noise margin high and noise margin low, and we have defined the noise margin high in this way and noise margin low in this way, right? And we have also mentioned that it is expected that noise margin high means both noise margin should be as high as possible as per your design. And at the same time, we have also seen that if the noise margins are not symmetrical, that is not good. We will try to design our gates such that the noise margins are symmetrical. For example, if the noise margins are 1 volt, then we will try to make both noise margin high and low to be around that only. Okay. Then we have just started our discussion on this regenerative property of inverter, but we could not finish, so we will start from here. So here, this is the regenerative property of inverter. Here you can see instead of 2, we have taken 3, just to illustrate the concept. So we have taken 3 and we have considered the input as V1. The first stage input is V1. The output of first stage is V1. So sorry, this is V0. This is V1. Second one, the output of the second stage is V2. Output of the third stage is V3. Right? So this is inverter. We do not know how we have made this inverter as of now. Say it is a resistive load inverter. Then in that case, the VTC would look something like this, the blue color, right? Try to follow this blue color. Okay, so for this inverter, this is the input and this is the output. So fine. So we have these characteristics, right? Now, if you consider the second inverter, that is this number 2 inverter, then for this inverter, this V1 is the input. So for this inverter number 1, V1 is the output. So V1 stays in this axis, right? In the y-axis. However, for this inverter 2, V1 is the input. So for if we want to plot the VTC on the same axis, okay, along with the VTC of this one, then how does that VTC of inverter 2 would look like in the same diagram? It would look probably something like this, right? Because now for this inverter 2, this is the input, right? And this is the output, right? So you can see when the input is low, right? See the output is high, right? Now when the input is high, see the output is low, right? So it would be like this only. So we have written to identify written is that inverse of this f of x. If this function is f of x, then it is inverse of f of x. Please let me know is there if you have any doubt that how we are getting this this particular function.
Sir, here we are assuming VOL bar as 0, right?
V
VOL bar.
V O L bar is 0. Okay. Yeah, that would be easier for us. Yeah, let us say that VOL dashed is 0. Right. Fine. And that is not difficult to design. We will see that. VOL dash can be made equal to 0. That is not an issue. Okay, so I hope then this part is clear how we are getting this. Okay, now say that we have applied here this V naught, right? And say the noise has been introduced, okay, at this first stage only, and that has corrupted the value. Okay, where suppose the V naught is expected to be 0.2 volt, but it has now become say 1 volt. So instead of this from here, it has shifted this to this, right? Okay, so input is now V naught. So you take this input from here to here, right? Right, see its reflection here on this, right? This will give you the output, right? See what will be the output means V1. See the output, take the reflection here, so the output is V1. Okay, fine. So output is V1, right? Fine. Now this V1 is the input for the next stage. Okay, so this is the input, right? So next stage VTC is this one, right? You remember, right? Next stage VTC is this one, and this is the input for this, right? So what will be the output? Take this here from here, take a reflection to here, right? So this is the output. So output of the second inverter, which is V2, is this much, right? Okay. So have you noticed something that gradually the error is decreasing? Maybe we will go see for this what is happening after one more gate. See, now this V2 is the input for V3. Again, V3 is for V3, this is the this VTC will be same as this of V1 because it is the alternate, right? This one, after this it has again changed. So V1 VTC would be the same as this of this blue one only, first one only, because if they are identical, right? So in that case, if you want to see what will be the output V3, then what will happen? You have to take another reflection from here and see this V3. So V3 is this one. Okay. So what I am trying to say from here is this one. See, when you have introduced this V naught, right? This V naught, it is expected to be logic 0, right? But it has so much deviation, this much deviation, right? Okay. Then once it passed to go to V1, see the deviation from this logic 1, this has reduced. Now when it passed to V2, see its deviation from again here, this has reduced. When it passed to V3, see it's again here, right? It is very close to near to this VDD level only, right? So this particular property is called the regenerative property. That means if the noise has been introduced at a if there is only one noise source, means that if the noise is only introduced here, okay, not after that, then gradually after passing through couple of gates, okay, this inverter will try to minimize the effect of noise, okay, which has initially been introduced, right? So this particular property is called the regenerative property of the inverter. This is not only the property of inverter, maybe some other digital gates also should have this property. So to have this property, regenerative property, this VTC should be like this. This V out versus V in characteristics, this should be like this. That means what? That means it should have some region, okay, where the slope is less than mod of slope is less than 1, right? These two region, slope is less than 1, and it should have some region where the slope is mod of slope is greater than 1. Okay, if you see this type of property in any VTC, then you can cross check and you will find that that particular gate would be regenerative in nature, right? Means it will
Sir?
gradually nullify the effect of noise. Yeah, do you have any question?
Yeah, sir. So if we increase the number of gates, the deviation would go on decreasing, right?
Right.
So, sir, is it possible to achieve a deviation of zero? I mean, V2 reaches the origin and V3 reaches the uh, this point.
Yeah, it actually, if you see that, V3 is now quite close to this VDD only, right? The highest level only, supply level. Right. Again, that also depends on, what is the characteristics of your VTC. Means, this here slope and curve, right? You can understand from here, right? That is going to reflect. If the here the slope is very less, then obviously, this is be quite close to this VDD only. Yes. So that way you can see there will be only two stable state for this type of gate. If you give any input, then after passing through, it can either go to this point or it can go to this point, right? If it is on this side, then gradually after passing through a couple of gates, it will go to this point, right? Or it can go to this point, right? So you can think in the other way as well. For example, let's say that you instead of this VTC to be like this, right? As shown in the blue, say the VTC is like this. Okay. So this is now this f of x. Okay. And this is that inverse function, inverse of f of x, right? So in that case, see, let us try to see what will happen. So say this has introduced, then this is V naught, right? Then V naught will, no, it will not be reflecting from there, right? It would be reflecting from here, right? This is the effects, no? So it will be reflecting from here, right? Okay. Then what will be the corresponding output? Corresponding output you will get from here. So now this will be V1, right? Now this V1, we have to see this V1 will go to where? Now V1 will be reflected from which place? Hey, if you have understood, you should be able to tell me.
So the pink one.
The pink one, which side? Top side or this side?
Sir, right side.
Right side. Okay. Then what will be this output? It will be here, right?
Bottom.
Right. So this is what? This is V2, right? Then after that, what will happen?
So again, it will go up to the green and then to the left the output.
It will go to the green and go to this left out, right? So as you can see from here, instead of you have given this V naught, but instead of coming to this place, it is actually diverging in the other way. So if this characteristics is not there, that is inside slope is greater than 1 and which is surrounded by two regions where the slopes are less than 1, if you introduce any noise, that noise eventually get amplified and propagate, okay, through the multiple number of gates, right? So is this clear to you? If it's clear to you, then we can move to the next part. Okay, so here we are going to do something interesting. And I request all of you to please have a pen and paper, means your copy and your pen in front of you, and please do it as we are, means as we are doing something here, please also do it in your pen and paper, because I am not going to write each and every line here. So I will ask you, so please find it out and you have to do it, right? So this is the task that we are going to do today. Okay, so if you do not have your pen and paper right now with you, please take it and make yourself ready. So here we are going to discuss about noise margin analysis in case of a resistive load inverter, right? So what's the big deal in that? It's not a big deal actually, but we have to see how to actually calculate, because if we can calculate for this for any other type of inverter also, we should be able to do that. So let us do for this one with more detail, so that we can skip some of the part from the next one, the next type of inverters, right? Okay. So this is the circuit diagram which we have already discussed. So here what we have to do, we have to calculate noise margin high, noise margin low, VOH dash, VOL dash. So how do you calculate noise margin high? Please tell me quickly. How do you calculate noise margin high?
VOH minus VIH.
VOH minus VIH. Thank you. And how do you calculate noise margin low?
VIL minus VOL.
Very good. Right. So we need these points, right, to be able to find this noise margin as well as VOH dash VOL. That means we need this. We have to find this, right? Then we need this, we need this, we need this, we need this, right? These are the voltages we have to find. Okay. Now, and we know that the VTC for this particular type of inverter would look something like this, right? Probably something like this. Yeah, we will try to figure it out. How correct is this? Okay. So now, and here we are not doing it type of numerical analysis. It's not a problem here, problem statement, but we are trying to find some generalized equation in the form of analytically only we're trying to find. Okay, so that if it is in terms of problem also, means numericals also, you can put those values and find it out. Not a big deal, right? So here, how should we approach, right? So the approach means here we have one MOSFET. So obviously we should know what is the current voltage equations of this particular MOSFET. And we have one resistance here, so which we already know, I into V means I into R will be equal to V, right? That is the Ohm's law. So we know that. So let us apply these concepts and try to find it out, right? And these different points. Okay. So before going to that particular derivation, let us see this MOSFET equations, right? What do you mean by this MOSFET equation? Yeah, well, you are studying this MOSFET equation maybe from your second year itself, right? Now, you know, in MOSFET, there are two regions. One is the linear region and the other is the saturation region. For example, you can see here, I have drawn it here, right? No, I need this one. So this is the linear region or triode region, right? And the next one, right, is from here. This is the saturation region. So this is the saturation region, and this is the linear region. And in linear region, diode equation can be MOSFET equation can be written in this way: ID equal to Kn dash W by L VGS minus VTH into VDS minus VDS square by 2, right? Where I hope you know on this, VGS is the gate to source voltage, VDS is drain to source voltage, VTH is the threshold voltage of this NMOS, and W by L, W is the width of the transistor, L is the length of this transistor, particular transistor. So this W by L is called the W by L ratio or the aspect ratio of that particular transistor. And here this Kn term also, you know, Kn term is nothing but it is It is mu n Cox. Mu n is the mobility of electron because it is n-channel MOSFET, into Cox is the capacitance of the gate, divided by area, right? The area of this means basically the per unit capacitance. This Cox stands for. So this is Kn dashed, and this is the process parameter, okay? Because if you fix the process, then this parameter is going to be fixed. It is not going to change. Only thing that is going to change is the W by L, depending on your design, all right? So technology, when you fix any technology, say 180 nanometer node, so 180 nanometer node, this Kn value is fixed. You are not going to change this. Only thing you are going to change is this W by L ratio in terms of your design. And when you are doing the operation, you are going to change VGS, VDS, all this stuff, right? Okay. So here, what is VGS for this linear? Here, VGS is obviously greater than threshold voltage. That's why the transistor is on. And the VDS is less than VGS minus VDS. You know that, right? It is below the saturation, like VD sat, right? So this is basically this VD sat, right? And in saturation, the equation will slightly change and it become Kn dash by 2 W by L VGS minus VTH squared. Here it is again for both case VGS is greater than VTH and VDS is greater than VGS minus VTH, right? Okay, this is just a recap. I know that you already know this thing very well and you are quite expert in that. Fine. So we now know this couple of things. Okay, now let us go to the analysis part and see how can we find this, these points. Let us say like we have to find, say first this point, VOH. So tell me, how do you find VOH?
dv out by d in minus 1
Right. And how do you find the dp out by dp in?
by case KVL.
By KVL. Okay, very good.
Dv out
So
in terms
basically what these points are, you can see like as we have discussed yesterday. So this is basically the transistor output characteristics and this is the load line. So depending on the resistance values, you can have two different load lines, right? And that will give you, how this VTC would look like basically, right? So as you can see for this pink one, right? If you change this V in, means as you are going from this side to this side, see the change in output voltage is quite gradual, right? Tick, 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 right? Whereas if you consider the green one, see the deviation. From when you go to V in, it is here. So directly it is coming from here to here. Then when you go to V2, it's V in 2, it is here. When you are going to V in 3, it is here. So the transition is quite fast, right, in terms of this output voltage for this green case. So that means this fall would be much faster for this green line, right, compared to this pink line. Okay, we will see all this in much more detail. So now, as your friend suggested, we have to find dv out by dv in based on this circuit, and so that we can find this VOH. So I request all of you.
Transition is faster for green or pink one, na? Because
Transition is faster for pink one. Okay, please then explain why it should be faster for pink one.
Because for certain change in voltage, the output voltage is making like
What is the
on the
output voltage?
x-axis.
Where is the output voltage?
Sorry.
Right? Here is this output voltage. V output is nothing but VDS. Yeah, I told yesterday, na? Wait, what is happening? These lines, where from these lines? Yeah. So this is what's happening. It is I am not even writing, but it is somehow started writing. Wait, just I do not know what is really happening here. The sensitivity has increased a lot. Now it's better. Yeah, now it's better. Yeah, so this is VDS, right? So the output voltage is basically VDS. Now tell me, for which case the VDS is changing faster, pink or green?
Sir, green one, sir.
Yes. Now Harsh, have you understood now?
Yes, sir.
Okay. So can we go to the next step?
Yes.
Okay. Let's do that. So again, I think I can draw the circuit once again, if that helps. So this is V out, this is VDS. So V out is basically VDS. This is V in. Okay. Now tell me, and we are now trying to find this point, right? This point where the slope is dV out by dV in is equal to -1. Yeah. So how should we approach? First, we know what is this current. Okay. So in this region, the transistor is operating in which region? Should we write the equation of the linear region or saturation region?
Linear region.
Linear region. Why linear region? Please explain.
So V in is small.
V in is small. Then V in is small. Will it be in a linear region? Then again, it is important to see this big figure. See here, V in is small here, right? V in is small here. And where is the intersection with this line? Here or here. So this is which region? Please tell me, this is which region? Saturation region. So here, this transistor would be in the saturation region, right? So we have to write the saturation, that equation. Kn dash W by L into VGS minus VTH. Oh, my writing is becoming so bad. Wait, I'll write it in a paper. So ID is equal to Kn dash by 2 W by L here VGS minus VTH square, right? Okay, so this equation we know. Okay, then can I write this V out, this output voltage, to be as VDD minus ID into R, right? Can I write it? I am not getting any response from your side.
Yes.
Okay, so now ID we can replace with this, right? Kn dash by 2 W by L. Now what is VGS? VGS is basically, this is gate, this is source, this is drain. So VGS is nothing but V in, right? So it is basically V in minus VTH square. Okay. Then now am I in a position to take the derivative dV out by dV in?
Sir, ID times R, you left R there.
Ah, very good. Right. This R was there, right? So R we have to write. Okay. So are you in a position now to take this dV out by dV in? Right. We can now. So dV in. Now please tell me what is going to happen here. So
minus Kn dash W by L.
yeah, minus Kn dash
L,
minus
W
Kn
by
dash
L.
W by L, right?
V in
V
minus
minus
VTH
VTH into R.
into R.
V in minus VTH into R. Okay. Right. So this is equal to what? At this point?
-1.
-1.
This point, this is -1. So when you are writing here -1, this V in is becoming what?
VIN.
VIN. Right. Okay. So actually, what was our motto? We wanted to find what?
VOH.
VOH. Okay. And okay, VOH at the same time, we also want VIN, or what am I writing? This VIL. Right. It is VIL. Right. So we have to find this VOH. can anyone tell me what should be the value of VOH?
VDD minus L by 2 WKM prime R. That R part I forgot.
You forgot means?
I mean, now I put, first we should find VIL and then substitute it in that
Okay,
equation also,
okay,
and then find
okay,
VOH.
okay. We will find first VIN. Yeah, VIL. Yeah, tell me what is the value of this VIL?
So L by W.
VIL would be
Directly substitute dv out by dv in the v out equation.
sorry.
In the v out equation, we can also directly substitute the value of dv out by dv. So because k in dash omega w by l v in minus vth into r is also present there.
Mm-hmm.
So we can substitute that and write vdd minus vdd plus v in minus vth by 2.
Hmm.
So
Anyway, we need VIL's expression finally for NM.
Yeah, so we need a VIL.
Better write for everything.
Right. We need VIL, right? So we have to keep this V in, right?
yes.
Yeah. Then please tell me what is the value, means what is the expression of, what will be the expression of this VIL?
So L by W. So
L by W.
1 by R K and dash plus VTH.
L by W. Are you saying this is got reversed? L by W?
Yes.
Yes.
Okay. L by W
1 by into 1 by R K and dash.
into 1 by
So yes, sir.
into 1 by
R
R
K and dash
K and dash
plus VTH.
plus. So here there will be any bracket?
No.
Or, no. VTH. Okay. Please all of you check whether you are convinced with this or not.
Yes, sir, it's fine.
It's fine?
Yes.
Okay. Okay. Let me see one thing here. Yeah. Now, I think one more small, I think I have not mentioned, but you know this part, but let me write it as well. So here you see this ID, right? This is Kn dash into W by L, right? Kn dash into W by L is nothing but Kn, right? So it is basically Kn by 2 into VGS minus VTH square, right? Similarly, you can also write this part as Kn, right? So that way, can I write this one as VIL is equal to this VTH plus 1 by RKN, right? I can write it now in this way.
Yes, sir.
Okay, fine. So that way our VIL, the expression of VIL, we are able to find. So this is this point VIL. This is also important, VIL. Now we wanted to find this VOH. Yeah. Now how you will find VOH?
Put in the V out equation.
So we have to find out ID and then find out V out.
Right. Maybe, as your friend said, you can you put it in this equation?
Yes.
Right. This is V out, right? Here this is V in. Now you have to put the V in value as VIL, means this one, and then you have to find what is the value of this, or what is the expression of V out. So could you please quickly do and tell me what is the value, means what is the expression that you are getting?
Sir, VTH minus 1 by 2 RKN.
VTH. Are you sure?
Oh, sorry, VDD minus 1 by
VDD. VDD minus 1 by 2 KNR. Please check. Are you getting this or not?
Yes, sir.
Yes, sir. Yes.
Okay. Okay. So two important points we have extracted from this. Right? Okay. Let me save it. Yeah. Now there is one. There are actually two other points, right? One is corresponding to this input and this output. Again, the same criteria. Right? Now here you have to be a bit careful. Which region the transistor is operating. You are getting my point? Now we have to find VOL and VIH, right? Now to find this out, we have to do again similar type of analysis, but while you are writing the equation of ID, you have to be careful in which region the transistor is operating. Now please tell me in which region the
Linear.
transistor would be operated here. Please tell me bit quickly.
Sir, can you repeat once more?
Yeah, sure. So I am saying now we have to, right. Now I'm saying that we have extracted these two value, right? Means these two expressions, right? This point and this point, right? But now we have to find this one and this one, right? So here the transistor is operating in which region? The question was this. So now we have to do for VIH and VOL. So the transistor is operating in which region? Any comment? Any idea? I thought you will be able to.
Linear region.
Linear region. Can you triode region, right? Can you tell me why? Why you think it should be in the linear region?
Very
Because
small value of VDS and high value of
high
VN.
value, and also see it is getting almost saturated right here in this region, right? So that is only possible the saturation when this line will be keep on touching this in the this region, right? Then only see this VDS will be getting saturated. See from here, this one, then it goes to this much, only small decrease, right? Then it goes to only this. So VDS is means VDS is basically the V out, right? So basically V out is decreasing, but the decrease rate of decreasing very small. So that's why in this region the transistor would be operating in the triode region. So we have to write the equation of the triode region here. So here it is ID would be equal to Kn K. Okay, let me write it in terms of Kn only. Why to write now W by L? So Kn into VGS minus VTH into VDS minus VDS square by 2. Right. Okay. So this is the thing, and obviously you know this V out, the same expression will be there. It is VDD minus IDR. Type of repetitive, right? The same thing we are doing it here, but still we need to do it. So please find, and after that find dv out, make the expression, make the expression of this dv out by dv in. So find dv out by dv in and make it equal to -1, right? Once you do that, you will find the value of what? You will find the value of, means both VOH and VIH. Sorry, VOL and VIH, right? VOL and VIH, right? Yeah. So could you please tell me what would be the value? Please do it. Please do it and tell me the expression of this VOL and VIH. Let's see who can do it first. Yeah, could you please tell me, like, what will be the value of this, like the expression of this VOL and VIH? Akshay, have you done that? Akshay Jain. Okay. Alisha?
So doing it now.
Okay. Okay, need some time, fine. Devraj?
Yes, sir. I am currently trying to figure it out, calculating.
Okay, so please do this. Can tell me quickly. Giridhar?
Sir, I'm doing it now.
Okay. Harsh?
Yes, sir. So little time.
Okay. Joel?
Yes, sir. I'm just doing it now.
Okay, please do it quickly. Jyoti Prakash? Jyoti Prakash?
Yes, sir. Once again, sir, try.
Shayan Maiti? Bikash PS? Jash Agrawal?
Yes, sir. I'm doing.
Ujjal?
Yes, sir. I'm doing it. I'm trying.
Okay, so please tell do it and tell me.
Yes, sir, I got that expression.
You got this similar type of expression?
Yes, sir. 2 VDD by 3.
Okay, very good, very good. Shubhayan. Okay, very good, Shubhayan. So others, please also do this. Do the complete process. You don't have to do this thing for each and every every inverter, right? So this is only like for at least for one, we should do it completely. Then Shubhayan, please try to find VIH.
So I found out, but it's a very complicated expression.
Yeah, it would be complicated, but can you simplify it?
So a little bit.
Okay, so please try.
So yes, sir. Something like Bishwashu wrote.
Okay, in that case, could you please also find the input voltage corresponding to this VIH? Now find VIH. So that means what you need, probably you can use this one, right? This expression. Now you know V out and can just replace
Yes, sir. I have
this.
written VIH.
So yes, sir. Something same, similar.
Similar, right? Yeah. this is KNR V out, then you can understand, right, how what will be the expression, right? Now you have to replace, right, replace this VOL in, like, VOL means basically now V out is basically here VOL, right? All V out would be equal to VOL, right? And for all VOL, you have to write this one and then find the value of this or expression of this VIN, which would be equal to this VIH, right? And I'm just writing the final expression. So if you do, it would be KNR plus 2 root over of this 2/3 VDD by KNR. Right? So this is the VIH and this is VOL. Right? So two other important points we have now. We are now able to extract. Right? Okay. So is this clear, like VIH? So then in that case, we can move and go to try to find the other 2 points. But I need your, like, are you, means, do you agree that is this fine? Then only we can move forward.
Yes, sir.
Yes, sir.
Okay, great. So in that case, the next 2 points, right? So the next 2 points, so let us mark, what are the points that we are able to find so far. So we have found this one, we have found this one, we found this one, we found this one. So with these 4 points, we are in a position to find noise margin high and noise margin low, right? Because, right, you can see the expression. So now we are in a position to find noise margin high and noise margin low, right? So now you have the expression. If the values are given, it's well and good. You can just put those values and find, right? So now find noise margin high and noise margin low, right? Because now you have everything, right? All the expression, just you have to do an subtraction from one value to the other value, right? Then you can find noise margin high and noise margin low. If values were given, you have to just replace those values and find the numerical value. Okay. So two other important points here we have to find. One is this point, right? One is this point, that is VOH dash, and the other one is VOL dash. Okay. Can you comment on the value or expression of VOH dash? Hello, can you comment on this VOH dash?
It's VDD.
It's VDD only, right? So no need to find it out, right? It is VDD only. It is VDD only. Very good. But what? Okay. Now can you comment on VOL dash like this? Can you comment on VOL dash? Now nobody is saying anything.
So just assume it as 0 maybe.
How can you?
Saturation.
How
Sir,
can you?
VD saturation.
VD saturation. How can you say that? I do not understand your like your logic.
Sir, here
Sir,
V
we
in
know that
equals
V in is
V.
VDD.
So we will put V in equal to VDD in the final expression which we got.
Okay. You mean this here, right? You mean here, right? Here, right?
Yes, this expression. Yes, sir.
Right here, right?
Yes.
So here, yeah, here this, right? This V in, you can replace this V in with VDD, right? And then try to find what is the value
Yep.
of V out, what is the expression of V out, and that will be basically the what? That would be basically your this VO
L dash.
L dash, right? So you see how these are quite a type of lengthy process, right? Right. Now, if you use some simulator, circuit simulator, okay, here all these type of these things can be done, all of it just within an just you have to type it. Means you have to type and just put enter, and immediately it will be calculated. Right, but if you do the hand calculation, see how big it is, right? And eventually, I would like to mention here one more point. See, this expression, these MOSFET equations are for the long channel MOSFET, right? Here, we have not considered the channel length modulation effect. Have you considered that? No. If you have to consider the channel length modulation effect, then we have to add one more term, lambda VDS, right? Then you see this VDS is basically V output. Now you think about the complexity that you are going to face if you are asked to incorporate the channel length modulation effect. This is one of the effect, but like that in practical MOSFET there will be so many short channel effects. There are so other many effects, right? Which are completely been ignored for the sake of simplicity of our calculation. So for hand calculations, we will do many of the times so many simplifications, right? So that if you do the hand calculation and find the result and try to match it with the simulation result, you will find there will be a good amount of mismatch between these two. However, for our understanding point of view, or from the logically thinking point of view, whatever we are doing, that makes sense, because we do not from our hand calculation, we do not want the exact answer, right? But what we want, the understanding process. For exact answer, we can always refer back to the simulator, circuit simulator, which will give us the accurate or perfect result if all the models are being properly incorporated. Okay. So in that case, I am assuming that you would be also able to find VOL dash. Okay, because it is just a simple process. Just you have to replace it and you will find it. Okay, good enough. So now I have a question. Say, consider, okay, let me write it. You also write it with me. Consider Kn dash, this is equal to 30 microamps per volt square. VTH threshold voltage is of 1 volt. VDD equal to 5 volt. Okay. Now I am asking, design a resistive load inverter with VOL dash would be equal to 0.2 volt. Have you understood what I have said? This is one small numerical example. So consider this Kn dash for the transistor that we will be using this, and VTH is this 1 volt, VDD supply voltage 5 volt, resistive load inverter. So that means basically this circuit only, right? Now we have to find the value of this resistance so that you can achieve this point. VOL dash would be nearly equal to 0.2 volt. So can you give me how you are going to approach for this? Any clue? Yes, I am waiting for your answer.
We will directly put the values in that equation.
Exactly. Which equation?
Vn equals, yes, this
This
pink.
equation. Okay. So in this equation, what you are going to do, you are just going to put the values, right?
And
Okay.
kn dash into W by L, we will actually have to find the
Kn
W.
dash into W by L, that you have to find it out, right? Okay. Okay. So maybe more general way would be to write this equation. See this. This is VDD, right? So this is ID. So can I write something like this? VDD minus VOL dash by R, because now here this is the V out, right? V out is now VOL dash. So VDD minus VOL dash by R. This would be equal to Kn dash W by L VDD minus VTH VOL dash minus VOL dash by 2. Can I write this?
Yes, sir.
So VOL dust whole square bit.
Square, square.
Right. You are absolutely right. Right. Yes. Right. So here you see this this value is given. This value is given. Kn value is also given. VDD value is given. VTH value is given. Yeah. All these values are given. Even here, this is given. This is given. Right. Okay. So this is quite general R1. So from here, if you do little bit manipulation, so probably what you will be getting is something like this. Could you please check if you just put the values? Okay. Are you getting this type of expression or not? Please check it out.
Sir, R value is not given.
Yeah. So that's why I have kept R as R only, right? R value and WL by L value is not given. Okay, so please try to find like whether whatever I have written is correct or not. I'm just coming back in a minute. Yes. So are you able to find this? Is this correct?
Yes,
Yes.
sir.
Yes. Yes, sir.
Okay. So if this is correct, then we can see from here that if we have to design such that VOL dash is 0.2, then this W by L into R should be equal to this, right? A particular value. Right. Now we can choose W by for different W by L ratio, right? And accordingly R will be changing. Means now we can set either W by L or the value of R, right? Accordingly the other parameter have to be changed. Right? If you agree with me, then okay, before that, I will also discuss one more thing here. That is this thing. Maybe this point I will discuss bit later on. That is important. That would be important, otherwise the sequence will break here. Right. So as you can see from here, W by L into R is this one, right? So we need to achieve this. Now, let us think this problem from a bit different perspective. Different perspective means, suppose we can choose W by L equal to 1 and R value as 205 kilo ohm. Fine. We will get this. We can take W by L as 2 and R value as 102.5 kilo ohm. Then also we will get this. But what would be the implication? Okay, if we choose this in our design, what would be the implication? If we choose this one, what would be the implication? Right? It cannot be like anything we can choose, and it will not have any implication in other place. Now, trying to understand from the right now from the power perspective. At this point, only the power perspective. All right. So, from power perspective, if you consider what is the power dissipation in this particular circuit, right? What is the power dissipation? Then this is a digital circuit, right? Either it can be operating in the logic 1, means logic 0, or logic 1, right? Logic 0 means here basically the 0 volt. 1 means it is basically the uh, either VDD or yeah, for this it is VDD only. And here logic 0 means basically close to 0 or it is 0.2 volt, right, as mentioned here, because you might think that this transistor, this inverter has been operate, this input has coming from the next another inverter, okay, which can supply not equal to 0 volt, but it can supply the minimum voltage is a 0.2 volt, right? So it cannot be maybe 0 or 0.2. Okay, and we are considering that 50% of the time this transistor would be given as 0 input, means 0 logic, and 50% of its time the transistor would be given as 1 input. Are you with me?
So can you repeat?
Ayushi? Okay. So okay, maybe I will write couple of things. Power dissipation. Right. Now here, or like we can choose like different, right? So from here we are writing which one to choose. Which one to choose. Right. Now we're writing considering power dissipation, okay, in the circuit. If we consider the power dissipation in the circuit, so for this we are taking couple of assumptions. The first assumption is input is low for 50% of its operation. Input is high for 50% of its operation. So that means, so if you are considering some time, for that much time, 50% of the time the input is 0, logic 0, and 50% of the time the input is logic 1. Now why it is important, that you will understand now only. See, when this V in is equal to 0, right? When this V in is equal to 0 means either 0 or 0.2, whatever you give here, right? The transistor threshold voltage is 1 volt. So the transistor is off. Then what would be the power dissipation in the circuit?
0.
0, right? So when input is 0, MOSFET is off, power 0, power dissipation 0, right? Okay. Now when the input is 1, what would be the power dissipation? Please tell me quickly.
ID square into
I square R plus BDS into I.
Yeah, that is true. But can you give me something better in this context, whatever we are discussing? Can you tell me in terms of VOL dash?
VOL dash into ID plus
VOL
ID.
dash into ID? No. See, when this here you have given 1, when you have given here 1, logic 1, right? So here the voltage is minimum. right? Voltage is minimum. So drop across this transistor is also minimum. It is
Yes.
around 0.2 volt, right? Then the maximum drop is occurring across this, which
Yes.
is 4.8 volt, right? So basically it is VDD minus VOL dash divided by
Whole square Maya.
right. Okay. Can I write? Okay, I have to find power dissipation. Can I write the current is this to this resistance?
Yes, sir. I told that.
Yes.
Oh, you
I,
told this part only?
I
Okay.
square R plus that.
Right, right. I square R. That is true. Right. Now here I is this one. So we can write this, or you can write I into V, right? So you can say like, supply voltage. This is the current, right? This much current is flowing through this, right? And supply voltage is VDD. So what will be the power dissipation? The power dissipation is VDD into VDD minus VOL dash by RL. Is this correct? Please tell me quickly. Is this correct? Dev Dotto?
Yes, sir.
Okay. Deepak, is this correct?
Yes, sir.
Okay, great. So if this is correct, fine. So this is the power dissipation in the when the input is 1, this is the power dissipation would be 0. When this input is 0, logic 0, right? Then what would be the average power dissipation? Just we can simply average power dissipation would be the average of this. DI PATI. So average would be VDD by 2 into VDD minus VOL dash by RL. Right? So this is the average power dissipation. Okay. So this is just we are doing something so that we can calculate what is the power dissipation. And at the same time, you can also see how we can actually find a power dissipation in this type of circuit, if it has been asked in any numerical problem. Okay. So if this part is fine to you, then let us come back here and to this question. Which one to choose? Because we have to now make this criteria, fulfill this criteria. So to fulfill this criteria, we have so many options, right? Okay. So for that, we will write here a couple of things and you have to tell me this one. So one is this W by L ratio. Other one is the value of this RL in kilo ohm. And other one is this DC power consumption in microwatt. Okay. Okay. So option number 1. First, what we have discussed, WL ratio 1. This is 205 kilo ohm. DC power dissipation. You have the expression. Please calculate and tell me. Please tell me.
$58.5 microwatt.
58.5 microwatt. Thank you. And that is absolutely correct. For the second one.
119.
119. What I got is around 117. Can you cross
So
check?
117.
117.
Yeah, 117.1. Yeah. For the third one. For the third one, quickly.
75.6. 175.6.
175.6. Okay. Next.
234.
4.1.
234. Yeah. I also got some in this same range. Yeah. For the last one.
292.7.
292.7. Yeah. So now we should be able to answer this question, right? What we have asked ourselves earlier. In this design, which of the combination to choose, right? So you can see, as we are increasing W by L ratio, so obviously we are decreasing this. We have to decrease this WL value, right? But what is happening? See the power, DC power consumption. DC power consumption increases, right? Increases. So if the power consumption is a major issue for your this particular design, or that is the primary concern, then you have to go for W by L ratio probably 1 and RL value to be 205. Again, I am saying if the minimization of power consumption is the main motto or the sole motto of your design. Else, if there are other things, then there will be a question of compromise that probably you can choose this one, maybe the next one, or maybe this one, right? So that the other parameter, for example, delay, or maybe some other parameter, that you can do some proper adjustment with that other parameter. But if it is a solely on the power consumption point of view, then you have to choose this first one. So, but whatever you choose, you are going to get V output VOL dash to be equal to 0.2. That is not going to change, right? The thing what is going to change is this one, the power distribution. So you are when you are designing any circuit, so it's not only from the one side you have to think that, I got this, so I can choose any value, but you should consider the other important parameters or other important performance indicators as well. One of the indicators is the power dissipation. So I hope with this example, I am able to give you a proper, give a quite a solid understanding, right? When you are considering any design issue, how you should approach.
Sir, we could have thought this as intuitively also in one way.
Right.
Like v OL dash is constant, we know, for any case.
Right.
Respective. So the voltage across resistor is fixed.
Right.
So we just have to check the current equations which involve only the W by L term. So the W by L term increase, the power consumption will increase.
Right. Very good, Harsh. Absolutely. I agree. I agree with you that we can also do the same analysis intuitively, like as you have suggested. Right. Okay. But here I wanted to give you this flavor so that, if you have to do it in terms of numerical analysis, then, you can do it in this way. Okay. Now here, what would be the issue? Issue in the sense, what would be the issue of choosing this big resistance? Okay, you can choose this W by L, no issue in that. Okay. But if you want to make this W by L this much, means not W by L, RL to be 205 kilo ohm, then you are going to have, you have to have pay some price. Now, what is that price? Price is to make or fabricate large resistor. Large resistors means large ohm, means large value of ohm. Okay, high means high resistance. Actually, resistor is the name of that component, right? And that's property is the resistance. So its value means its resistance is higher. So if you have to make this fabricate, you need very large area, right? Which VLSI does not allow you. VLSI means very large scale integration. So to make one register, if you take large area, then your integration density would become very small. Then probably you will be in the LSI range, right? Only the large scale integration, or not the VLSI, right? So how large this area might be? I can give you one numerical example, maybe just after some time, so that you can get an idea what is the transistor dimension, and compared to that, if you make a resistor, what would be the dimension of that, okay, to make one inverter. Fine. So in VLSI, very large area, not possible. So ultimately, this high resistance value, if you do it, you cannot incorporate in a proper VLSI circuit. Right? Now, there will be one more issue for choosing high value of resistor. 1 minute. So maybe I can write one more thing. Now,
Sir,
issues of high.
Sir, what about I square R losses?
I square R losses means?
Sir, if the value of resistance is high, then there would be heating issues also, right?
There would be heating issues also, right?
So that could be an issue.
Yeah, but
so, but in the expression of I, R is in the denominator, right? So for one, the heating issue would be actually less because less power is being consumed.
Right, and at the same time, there is one more component, which is the transistor, right? Right, the transistor will allow the current, right? So the same current what is flowing through the resistance, the same current has to be flown through the. Anyway, you will see those things, later on. So yeah, so issues of this using high RL. So first thing is that this area. Okay, what is the next issue that also you will understand now? See, this circuit is something like this, na? This is the load capacitor. Suppose it is driving another inverter from VDD. This RL, this is the capacitor, right? So when it is charging like this, right? So the charging time constant is RL into C, right? When it is discharging through this MOSFET, right? So the MOSFET, if you choose this one as very high, so the charging time of this capacitor would become extremely high compared to the discharging time. So that means the switching cycle will also become type of asymmetrical, right? The charging is very long, discharging is quite fast, right? So later on when we discuss this type of delay, then we will also see that it is desirable to have the rise time as well as the fall time as close, means in the similar range, right? So maybe we can write this point here as well. So this is number 1 point, this is number 2 point, asymmetrical switching characteristics. Asymmetrical switching characteristics. Fine. Okay. Now let us come to the next part, again to the area part. Okay, maybe before that area, I want to discuss maybe here one more thing. Yes. I hope you are still with me. I have not lost my audience, right? Is the class still with me?
Yes, sir.
Yes, sir.
Okay, thank you. So, this is again not actually this issues is one topic. This topic is now this is finished. Huh? So we are now discussing another thing. So regarding the VTC. So this is V out, this is V in. Okay, right. So we have seen that the VTC can be like this, right? VTC can be like this, or eventually VTC can be like this. So can you comment for this number 1, 2, and number 3? For these 3 cases, what is the value of this Kn into R comparatively? Suppose if you say this KNR1, KNR2, KNR3. So can you give me some idea? I think you should be able to give it quite quickly
One is
because
than 2 less than 3.
uh-huh.
So 1 is less than 2 is less than 3.
One is less than okay, you are, as per you, this is the relation, right? Tarun, is this right?
Yes, sir.
Okay. So why do you think so? This is right?
So I saw the equation of VIL and VIH, and so if they are low, it means that the curve is more steeper.
If they are low, the curve is more steeper. You means the slope in particularly this region?
Yes, sir.
Okay.
So for curve 3, VIH and VIL, it will be
right.
And like VIH and VIL, they are like inversely dependent on KMR.
Right. Very good. So you can see the tone is absolutely right. If you have to see there's a slope in this region. So first you have to tell me that this region, which is highlighted region, the transistor is operating in which region? Yeah, class?
Saturation.
The transistor is operating in the saturation region, right? Okay. So that is then the same thing that we have started our discussion here. The transistor is in saturation. So you can see the transistor is in saturation. And using this, we have found what is this dV out by dV in, right? So you can see this is basically Kn, right? Kn into R, right? So you can clearly see from here, then dV out by dV in, which is nothing but the slope, is proportional to this Kn into R. So more will be the Kn into R, more is going to be the slope, right? So that way also you can explain that for this particular case, if you increase Kn into R, then this curves in that particular transition region is going to be much more, or this, their slopes will keep on increase, right? All right. Okay, so this is from the equation point of view, right? But can you give me something like its physical meaning, right? Why, if I increase Kn, suppose if I increase Kn, then obviously Knr value increases, then I will move to this side, the transition will be faster. Or if I increase R, why the transition would be faster? Okay, the second answer to your second question, that is, if you increase R, then why the transition would be faster? I think I have already discussed today at the beginning, right? If you see this, right? Can you give me a comment for this green and this pink, where the resistance value is higher?
Green one.
Green one. So say it's R1, say R2. Then here R1 is greater than R2, right? And we have already discussed for this green one, the transition will be much faster, because you can see here, the change is like here, then here, then here, then here, like that. But for green one, see, from here to here, that means this much, then from here to here, this much, then from here to here, this much. So that gives you that idea, right? So if you increase the resistance value, why you are expecting that the transition will be faster in that particular region, right? So that gives you that explanation. But still it is not clear how Kn value would increase this transition. Can anyone explain?
So Kn equal to mu n into W by L, and mu
Right.
n is actually the mobility. So if the mobility increases, obviously.
No, mobility is actually constant. I told you, na, Kn mu n into Cox. This is a process parameter. So this is not dependent on the design. Okay. So if when you choose the technology, this is fixed.
Okay.
So only thing that you can change is W by L. Yeah, from this point, try to think why.
So the
If
will
W
increase if gain increases and
Kn increases, yes. Then, yeah, I think you are in a
and
right
the
path.
and the then the drop of voltage will also increase faster.
So
For
V out is
Drop,
equal
yes,
to
yes.
VDD
I think
minus
right,
IDR, and in
right.
ID there is Kn, and so like if KNR is higher, the drop would be faster.
Right. See, here you can easily explain from here. See, this is the suppose the two characteristics earlier, right? And here, let us say this was that uh, load line. Okay, so for this case, load line is fixed. So, so this is right because it is VDD by R. So this position is fixed, and this is VDD. This position is fixed. So only moving things is like these points, right? Now you have suppose increase this Kn means W by L ratio. So for V in one, right? So for V in one, your current has increased. For V in two, your current has increased, right? See now where the cross sections are. Now the cross sections are here to here. So that means when you have changed, so earlier from 0 to V in, you are getting a change up to this in the V out. But now from here, for the same thing, see, this both lines corresponds to V in 1, means VGS, right? Only thing is that now you have increased the W by L ratio, your current has increased. So the cross section point has changed. So see the change, the change is now much more compared to the previous one. So if you increase this Kn, your shift is now much more, right? It's just moving very fast to this end. So you can think this way also, right? Physically, right? That is the reason why KNR means if you increase R, that we have explained why. Now, if you increase Kn, why? That slope is expected to increase. Is this part clear to you? Hey, I am not getting any response. What is this? Ayushi, Oritro, Oniket, Omit.
So it's okay.
Yes, sir.
Then why I am not getting any response? Okay. Then let us move to that large area resistance part, right? A little bit discussion on that, why it is challenging, and give you some idea why means what will be the area required to implement that particular range of resistance. Huh? Okay. So cheap area. So cheap area, particularly we have two components, right? Components we have only this MOSFET as of now, and the other one is this resistor RL. So MOSFET area is given by this simple thing W by L, right? And this RL, we will discuss that. Now, what is L? L is the length, W is the width. So length is fixed for a particular technology node. So if you are choosing 180 nanometer, then you have fixed your gate length. You are not going to change it. You can't say that, I make a transistor in this chip with a gate length of 180 nanometer, another transistor with 240 nanometer. No, that is not allowed. Your gate length should be same for a particular technology node. What you can do, rather you can increase the width. You can play with the width. So width is this. So if you are thinking about the technology node, so it is 180 nanometer. 180 nanometer means 0.18 micrometer, right? So 0.18 micrometer, if it is L value is W value is also 1, so W is also 0.18 micrometer. Then you can multiply these two and get the area, right? Okay. Now, what about the register? Register, before going to the discussion on the area required to make and register, let us first discuss how these registers are made.
Sir, can you clarify particular tech model in first point again? What do you mean by particular tech model?
Okay. Take node actually, not mode. Okay. Particular technology node. Particular technology node means, suppose when you are designing any circuit, you have to first decide, like I'm going to design it at 180 nanometer technology node. Okay, later we will discuss what do we mean by this 180 nanometer technology, but as of now, you can think that 180 nanometer would be closer to that of this gate length. Okay, for this. So gate length would be around this. But again, I think this is not very correct way to say that. Okay, so you can say that, close to that. This gate length is 180 nanometer for that. But similarly, one of your friend can say, no, I'm going to do it at 140 nanometer. Right. Right. Provided you have the fabrication facility of both 180 nanometer, 150 nanometer, you can choose any one of them. Right. But once you choose 180 nanometer, you have to fix with 180 nanometer. Right. Then you say, like, 180 nanometer technology node, I can make a gate length of 180 nanometer, also 150 nanometer, maybe 200 nanometer, 250 nanometer, whatever I want. No, that is not allowed. So by saying the particular technology node means the process, the fabrication technology I am referring to. Okay. Suppose once you have design, then you have to give that design to a fabrication engineer, right? So fabrication engineer will take the design and make the real life device, or make the real life circuit, right? So there, from the technological point of view, fabrication point of view, they will specify some rules, right? If you are designing with our 180 nanometer technology, then you have to give this much space, this much length, this should be the separation between this and this, right? All these things, we'll briefly cover, okay, for some of the technology nodes. And so all the details will be there and they are fixed. Okay, so you cannot choose as of like as you wish. They are given by the foundry, those by the technology guys, mean the fabrication guys who really fabricate those devices. And as a designer, you will be designing, you will be taking care of this node, means you will be abide by those rules and design your circuit accordingly. Is this clear? What do you mean by particular technology node?
So a single company can design only one type of length only?
No, it depends. Suppose in TSMC, it can design, it can go up to 20 nanometer, 10 nanometer as well. But if you want to fabricate something in 10 nanometer range, suppose you need, as a suppose, how to explain it? Suppose you are doing some research, okay, and you need suppose 10 chips, only 10 chips. So you can contact the foundry and say, like, I need 10 chips. Okay, fine. They will say, like, which technology node? You say, like, 10 nanometer technology. Okay, fine. They might charge you, say, 100x. Say, just 100x. I do not know what will be the x. I don't know, 100x. Okay, then you say, like, I do not have that budget. Then they will suggest, okay, then why don't you go to consider 180 nanometer? Then when you say, like, okay, 180 nanometer still works for me, then they will probably charge you, say, maybe 4 or 5x. So they have the multiple technology nodes, a particular company, they can have. I'm not saying every company has that. Some of the fab has that. But when you go for a higher technology node, it is means gate length is bit larger. There the cost is bit low. When you go for the lower and lower technology node, cost will be in the higher side, and you need to pay more. Okay, but suppose think of the situation. And okay, now while you want to go for the lower technology node, because your transistor size will be smaller, device will be faster, less heat, all these things, right? But at the same time, you need only 10 chips, right? So no point of making it that to 10 nanometer, you can still survive with 180 nanometer. The basic operation can be done. But suppose if you are a manufacturer, suppose mobile manufacturer, okay, you need suppose 1 million chips. Then obviously, then if you go and ask them how much price I have to give, maybe for 1 million chip, they may say like, say 1 million X. Whereas you say, I want to do it for 180 nanometer, what will be the cost? Then they will might say 0.5 million X, right? So when you are going for a bulk, then the cost will be much lower compared to when you are going for a smaller quantity. So for smaller quantity, it's advisable you go for bit higher gate length. When you need a bulk uh, means bulk chip, then go for the smaller dimension. If you're obviously, it is not desired. Suppose if you are making some clock, okay, digital clock, and you are saying that, okay, I need 10 nanometer, because for your basic digital clock, okay, 180 nanometer is more than sufficient. You don't have to invest in 10 nanometer. 10 nanometer all will be doing almost the same thing, right? So there are so many things, inside. Your performance cost is one of the very important factor that as a designer you should always keep in your mind. Yes, Harsh, is this part clear?
Yes, sir.
Okay. So then how RL is made? There are two techniques by which it can be made. One is diffused resistor. Other one is polysilicon resistor. So diffuse resistors mean, suppose you have silicon, then you diffuse inside this silicon some region, say this N plus type, right? Then you make a contact here, right? And connect these two contact here, right? That basically a resistance, right? This is nothing but a resistance in between. So you make a diffusion and made the resistance accordingly. So maybe it is a P silicon, right? So it is basically the diffused resistor. So this is a diffusion process. So obviously this is the cross-sectional view, right? This is the cross-sectional view. If you see from the top, right? So this is cross-sectional view. If you see the top view, then probably it would look something like this, right? These are these two contacts, and these are the diffused region, right? So this is that N region, and this is that P region, and these are these two contacts, right? So here, two important things are here for this diffuse resistor. Sheet resistance can vary from 20 to 100 ohm per square. This sheet resistance might be a new term for you. Give me some time, I will explain what do you mean by sheet resistance. And sheet resistance is the term that in semiconductor industry in many places you are going to see or you are going to find. Okay, so just remember it that for sheet, if you want to make this doping and change this doping, obviously you can, if you make the doping higher and higher, then obviously the sheet resistance will become lower and lower, right? If you reduce the doping, then your sheet resistance will become higher and higher, right? Whereas for polysilicon, how it has been made? So for polysilicon, it is something like this. You have a silicon wafer, then on top of which you deposit a polysilicon, say of N type or maybe P type, that is depending on use, and make a contact between these two terminals, right? So that is basically a resistance, and maybe this is a P silicon, right? So again, this is the cross-sectional view, CS view. If you see the top view, then it would look like something like this, right? This is that poly part, polysilicon. Polysilicon means polycrystalline silicon. I think in your devices course you have learned this. What is the difference between crystalline silicon and polysilicon amorphous silicon, right? So here you can also from here you can see this is deposited on top of silicon. This is not deposited, this is diffused. So it is inside that silicon, but it is on top of that, right? But here it is on top of this, and you have made a contact out of this. So for this, the sheet resistance is in the range of 20 to 40 ohm per square, right? This is the typical the value that is you are going to see for polysilicon based resistor. But here one thing is that like for to make this polysilicon resistor, you have to make a like deposit polysilicon, right? Then etch the polysilicon accordingly and then make contact. And here you have to do a diffusion, make this region n type and then make a contact for this. And for this diffusion type, right, as this there is a particular limit, like what would be the minimum width of this diffusion length, right? So that if you consider that would be in the range of micrometer. So you cannot really go below this. It's tough to go to this width. Okay, this width, right? So if we have to consider this, you have to also consider that this width will be around a micrometer, say 1 micrometer, maybe more, right? So depending on the length, depending on the resistance, you have to increase the length, right? Suppose you need a higher length, then this length will increase, right? It will become something like this. If you need a lower resistance, this length will just move up and down for resistance to move up and down. I hope this small part is clear to you. Now let us discuss about what do I mean by this sheet resistance. So sheet resistance means sheet resistance is the measure of resistance of thin film that are normally uniform in thickness, right? So say you consider one thin film. So let me draw a type of a 3D diagram, whatever the way I can do. Yeah. So say this is that, right? And say the current is flowing from this direction to this direction, right? And here this, so if the current is flowing in this direction, so the length obviously is going to be, this is going to be the length, right? And this is, if this is going to be the length, then the width will be the diagonal way, and not diagonal way, this other, this side, right? So this is width, and this is the thickness of the slab, right? So what do you mean by sheet resistance? Sheet resistance is a measure of resistance of thin film that are normally uniform in thickness. Okay, so it is expected that this thickness is uniform, means throughout this it is T, right? Then how do you define resistance? Okay, this resistance, if the current is flowing like this, then resistance is obviously, it is basically rho L by A, right? It is well known. Rho is the what? Rho is the this resistivity, right? Okay. So, and what is A? A is the area, right? So area means what? Area is this area, right? Through which the current is flowing. So if I have to write it, the area in here, then it is basically W into T, or this T into W, right? So I will write it in this way rather, L by W. Then this particular rho by T means resistivity per unit thickness is the sheet resistance. Sheet resistance into L by W. Then if you see, then what will be the unit? Expected unit. See, this is resistance, so its unit is ohm. This is L by W, length by length, so no unit. So RS is also expected to have unit of ohm. right? But to differentiate it with the normal resistance, what we say, it is ohm per square. Ohm per square. So this is the unit. So you understand? Its expected unit is ohm, but to differentiate it with the normal resistance, we say it as ohm per square. Now, why say per square? Because see here, what is the important thing from this? R is equal to, this is the sheet resistance. R is equal to RS into W by L, right? Let's say L is equal to 1 mm, so that's W, okay? Then R is equal to RS, right? Okay, now say L is equal to 2 mm, so that's W. Then also R resistance is equal to RS. So that means if you are having a square, so maybe the square is like this, or maybe the square is like this, right? For both of them, the resistance value is same. So let me repeat it again. The resistance value is same for this and this square, right? So as long as your W and L value, they are same, W is equal to L, the resistance offered by this slab is going to be the same, right? So then if you fix the width, this width to say 1 micrometer, then this length is 1 micrometer, right? Then the resistance offered by this block is RS. When you keep one more box beside it, this also offers RS. So now if you measure resistance between here and here, then you have a resistance of 2 RS, right? But if you see only for this, it is RS, right? Similarly, suppose your friend has made a box like this and a box like this with the same material, right? Then also, if he or she connects and measure the resistance between these two, he or she will also find that its resistance is 2 RS, right? So that's how this sheet resistance is been defined in semiconductor industry. So with this, I think it is almost 12. So you might have some next, you definitely have some class. Do you have any class from 12?
Yes, sir.
Yes, sir. Okay, so that I told you one small numerical part that is left. Maybe that would have taken 5 minutes, but yeah, unfortunately we could not do it. So we'll do it in the next class, and we'll show from there that what would be the expected length to make a resistance of say this one here, right? This one, 205 kilo ohm. Okay, something like this. Then what will be the length? Okay, so maybe then with this we will stop our discussion here. So then I will see you in the next class. So please do study and read. Okay, after each day's class you should prepare those lessons by that day itself. Okay, don't leave it for the exam. Okay.
So you are going to upload these notes, right?
Yes, yes. Today I will upload both for the first one and the today's one. Huh? Okay then. Thank you.
Thank you.
So
Thanks.